The next reaction we're going to talk about is the halogenation reaction, where either bromine or chlorine is added across a pi bond. This results in an anti-addition and a racemic mixture. So if we take our standard electrophilic addition, in this case we're going to add just a halogen, again bromine or chlorine. Fluorine reacts too violently while iodine reacts too slowly, so we have the sweet spot of bromine or chlorine, and this gets added to either end of the pi bond here. So let's take this example and think about the mechanism. Because bromine and chlorine are polarizable, there are circumstances where the electron density will shift and one of the bromines will be slightly more positive and the other one will be slightly more negative. When this occurs, the nucleophilic pi bond can attack the more positive end and kick off the other bromine. When this occurs, we're going to be generating a carbocation. But because bromine does have a lot of electron density, what it can do at the same time is it can stabilize that carbocation by adding electron density to the other carbon. What this results in this case, is a bromonium ion, where the bromine is attached to both of these carbons and we have this three-membered ring. After this is formed, we will have the bromide, which was kicked off originally right here. It will now come in and do an SN2 reaction, a backside attack. So this bromine will come in and attack from the bottom, the backside. This three-membered ring with a positive charge will open up, and we result in the formation of an anti-product, where the bromines are on opposite faces. Now let's give an example where the racemic mixture comes into play. Say we have this example, where we have this alkene and the bromine is added. Notice the two bromine atoms in each of these are anti, so they're on opposite faces from each other. Why would we see these two products here? Why do we have a racemic mixture? Well, the bromonium, when it's formed, the bromine can either add in from the top, forcing the methyl group down, or it can add in from the bottom, forcing the methyl group up. The bromide ion will then attack from the opposite face, giving us our anti-addition. There's a modification of the halogenation reaction called a Halohydrin reaction, where we're going to add this halogen again, but we're also going to add a hydroxyl group instead of the second halogen. So in this case, we need to have a large excess of water for this reaction to proceed. Why is that? Again, let's go through the mechanism. Just as before, the alkene can attack one of the bromines, generating a bromide, and the lone pair on the bromine can reform here to make our bromonium ion. Now, normally the bromide would come in and open up this ring, but in the case of water as the solvent, there are so many more water molecules that are going to react instead. In this case, the water will come in and perform a backside attack, opening up our ring. This will generate an anti-addition, where the hydroxyl group is on the opposite face from the bromine, and we've got this extra proton on the water. This can be removed when we add the bromide. It can act as a base, grabbing that proton and eliminating this positive charge to give us the final product, where we have the bromine and the hydroxyl group on opposite faces. Unlike halogenation reactions, halohydrin reactions are regioselective, which means the formation of the products depends on the Unlike halogenation reactions, halohydrin reactions are regioselective. The hydroxyl group will be located at the more substituted carbon. So let's think about why that occurs. First off, we're going to generate our bromonium ion. This is very similar to our mercurinium ion, where we have a resonance form, where this ring opens up and we generate a positive charge at the more substituted site. Because this carbon here has a more positive charge, any nucleophile will be more attracted to that carbon. So when we add in our water, it will actually attack the more substituted site and open up the ring this way. When that occurs, we will have the backside attack. So if the bromine was in the front here going up, the hydroxyl group will attack from the bottom, which forces the methyl group up, and the ring will just open up. So now we have our anti-addition. The bromide that's left over will come in, grab this proton, alleviate this positive charge, and give us our product. Now remember that the bromonium ion can form where it's either wedges like this or dashes, so we will also get the other enantiomer as well. To summarize, Both halogenation and halohydrin reactions proceed via this electrophilic addition mechanism. Halogenation will add two halogens across a pi bond, while a halohydrin reaction will add a hydroxyl group instead of one of the halogens. Halogenation and halohydrin reactions both proceed via an anti-addition and will generate two stereoisomers. But halohydrin reactions are regioselective, where the hydroxyl group will appear at the more substituted carbon.